so much for coming out and sharing the interesting, amazing stuff you're doing with machine learning. And everyone knows Danny. I mean, do I have to introduce you?
That's okay.
He's the best guy around. Danny Silver, Dr. Danny Silver.
Thank you very much. Okay, hopefully my little flicker's going to work here. Yeah, I wasn't told I was going to be on camera there. I worked on my Einstein hair a bit more. Okay, so this is going to be much more, it does say machine learning, but it's going to be much more data mining type of talk, a lot of practical sort of applied things. There's going to be a fair mention of some technology in here, but when we get to that, I'll try to describe it for the for the general audience. And there's along the way, there's a few things that will come up I think you'll find really quite interesting that you'll all appreciate. Some things that maybe you hadn't thought about in this space. I know, and along the way of solving these problems, we encountered them and had to find solutions, and it was interesting to realize that the problems actually existed. So I'm just going to give you a quick little intro to what IDA is about. Set up kind of the typical problem space generally, and then there's a whole collection of things that you can see here that I'll go through, and kind of at the 500-foot level, everything from classifying phishing activity, which is a fairly recent one worked on with a student who was at Acadia, is now at Dal, building energy management and predicting solar energy at any point in the planet, and water flow rate and aquifer well level recharge predictions, cantaloupe melon yield, which a number of people here probably know about that one, Andy Vermeulen's farm, and then image classification or counting with some machine learning types of technology. So IDA has been around since really formally January of 2014, and our objectives fall into the three broad categories of collaborative and interdisciplinary research, and really focusing on everything from applying data analytics methods, and by that, of course, I mean the collection of data, preparing it, visualizing it, developing predictive models, and then finding new knowledge and getting that out to people. And how you disseminate that even becomes an issue. So it encompasses a broad set of the computer science and mathematical skills, certainly. So fostering that, in one of the areas we haven't done a lot, and we need to, and when I say we, I should introduce Christian. If you haven't met Christian Frye already, he's kind of the guy that's here all the time in IDA full-time. I'm kind of more part-time in many ways. The social science area is one of the spaces where we can locally do a lot more, and that's one of my goals over this coming year. Application and commercialization of products and ideas that come out of it, and new startups, and we've got two or three that have been working away here in this center. Education and training, and promotion and outreach to new folks, and there might be a mixture of all these people here tonight. So let's have a look at just your typical domain. So I don't know how many people know, but every large vessel now in the world actually has an automated identification system on it that goes ping, ping, ping. And it's seen as a really important thing. As this picture shows, you've got a vessel moving along, two vessels. They both have the AIS technology on board. They can transmit to satellites, kind of the inverse of the GPS, or to land-based stations. And predominantly, I guess the transmission is to land-based stations or buoys in the water and that type of thing. And those devices will then kind of put it on the internet, if you like, and gets it off to various centers. So then rebroadcast it to satellites. And that means that this vessel over here can know that this vessel is moving along at this rate of speed and avoid it, most importantly. Or if they're working together on something like the military, they could use it that way too. So it's very helpful close to ports. It's also very helpful in the broad ocean, so you're not running into things with or without radar. So it's quite an advance. But it sends timestamp, the vessel position, the vessel's identity, speed and course type of information, and sundry other little bits and pieces. And as you can imagine, you can use that to work on several problems. And that's what Stan Matwin and his group at Dal. Stan is the director of the Big Data Institute there. Questions like what type of vessel is it? Can you predict that from the movement of the data? Current activity, what's it doing? Is it operational at the moment? If it's a fishing boat, is it fishing, or is it going to a fishing area? What's its next likely action in this sequence? And the probability of intersection, which is a really interesting problem, because there's only 2 reasons why 2 vessels meet in the open ocean, and neither one of them are good. Let's think about that one. Okay, so here's a little snapshot of one bit of AIS data. I don't even know what shoreline it's off of here, but this is a fishing vessel, and the green points are where it's going out to fish, and the red are actually, it's a long-haul trawler, and it's actually fishing in this approach, going back and forth over a fishing zone. And we can frame the problem here if we're trying to identify whether it's fishing or not. It's just one of those classes of problems. As either looking at it as being what's called a structured predictive problem, in which we might take, say, 4 of these together and just take information from each of those 4 points and ask the question, well, is it generally fishing at that time? Like in the midpoint, is it fishing? And then take another 4 and ask, is it fishing? Or we can structure it as a time series, almost like trying to predict a stock, right? Values. What's the next value it's going to be? That might be for another kind of problem. Or we could just take and recognize this almost like a character. Is this an image of a fishing boat going out and then fishing, or is it all fishing, or is it just going out to fish? You know that. So you can kind of transform these problems into different things. In which case we could use image recognition, right? Different approach to it. So all those types of things could be tried depending on the problem. The some of the challenges the data presents is that we've got a mix of both, in this case, temporal and spatial data. And you know, that means that you have to do some preparation of the data oftentimes to deal with those variances that are occurring. And temporal variance, as you can see here, assuming that the vessel is traveling at the same rate of speed, just to this point, the data is arriving to us, or it's being sent, I guess, from the vessel at different points in time. It isn't periodic necessarily. Depends on a number of things. It may have tried to transmit here, for example, but it just didn't get out. Those kind of things can happen. Which is going to be a bit of a theme here. Oftentimes, in practice, when you go to use these machine learning data mining methods, you're faced with the problem that a key input parameter for predicting something didn't show up. The weather station didn't deliver the temperature. No, the whole thing is missing, you know, from the chicken barn or something like this, whatever you're going to use that for. So you have to be able to deal with these temporal variances and replace data if it happens to be missing in a sensible way. And then, of course, we've got some spatial variance that can happen here too. Like if we want to recognize that as a character, like the character A, B, or C, every one of us will write the characters A, B, and C slightly different, but any one of us here could recognize any one of our A, B's, and C's, generally speaking. And the variance doesn't seem to bother us, but it tends to be a big problem for one who wants machine learning. I mean, that's the point of machine learning, is to deal with those things. But there's some particular problems with this kind of data. And the last one is that the data is coming in sequentially, so time is a key element here. But it's not necessarily periodic. And there can be loops in the data, there can be all kinds of signatures potentially in the data, but we got to tease that out of this sequence of things that's occurring. So just picking on one of those techniques, just to give you a sense of what we could do in terms of classifying fishing activity. And this was work that Sean and Al, who was at Acadia, has done. He proposed the following. You take these are the raw AIS points, and what he does is interpolates, just linear interpolation between them, just drawing a line from one point to the next, and then takes that and makes it an image. This is just pixelization of this. If you can imagine, just lay a grid over top of this, and you just color in dark every pixel that's on the line, and everyone that's not on the line, it's a 0, and now you've got zeros in one pixel image. And then you just say, does that look like they're fishing or not fishing? And it's that, you train your machine learning image recognizer on that. And that's one approach to this. And it turns out that that really simple approach works pretty good. I mean, for simple things, here's non-fishing. They all just look like lines. They're going out to some place or they're returning. Whereas all of these little things look like you would expect, like fishing activities. Now, it's not as straightforward as that, because if you back up here to this image, of course, the question is where do you start on this to collect a subset of it as the frame of reference, right? Like if you start here, clearly this is, and go to here, that's non-fishing. But if you start here and go down to here, somewhere's a collection of both of them, right? Framing the problem is challenging. Oops, let's go back. Okay, so I'm going to start going through just a myriad of different problems that we've worked on. This is we're working with a company in Dartmouth on Green Power Labs, and they're located in the NSBI. Novacor, sorry, forgive me. Yeah, NSBI is in Halifax. Yes, in Dartmouth and Novacor. And I think they continue to do well. I haven't heard as much about them in the last year or so, but I think they continue to do well in the solar energy space. Their problem is, they gave it to us, was to predict essentially how much energy is focused from the sun at a point on the planet. It's actually called the global horizontal irradiance. That's what GHI stands for. And they wanted to be able to predict 5 to 120 minutes out from now how much energy is there going to be in our directed at our solar power plant. Now, the reason why they're in this business is because they can help people determine where they set up their solar plants, and they can, more importantly, tell them once they're set up how much energy they're about to produce over the course of the next few minutes through literally days. Turns out the Power Corporation, if you're interested in the power generation business, doesn't seem to be the easiest bunch of fellows to deal with, because you have to tell them how much energy you're going to dump onto the grid. And if you dump it on exactly as you said you're about to do over the course of the next 15 minutes to the next week, they'll pay you really good money. But if you apply too little or too much, they'll pay you less in both cases. And that's because there's no sink in the grid, right? There's no place to dump the extra energy. It actually costs them money to deal with that. So they send that back to you as a reduced rate, so they'll pay you. So there's a lot of value in being able to predict literally minute by minute. So we had a lot of data. This is representing kind of a subset originally, but at least 10,000 records from 3 sites. This is 5-minute interval data that was spread over a number of years. And it consisted of the time, which of course is really important. If you take away the clouds around the Earth, the problem is really simple. If you're trying to predict the amount of sunlight hitting a point on the moon or Mars, well, Mars has got some clouds too, but I assume it doesn't. And it's really easy. It's just geometry. But you add in the clouds and the particulate that's in the atmosphere of the Earth, it becomes quite a challenge. So that means we add in some satellite information and weather data, and most importantly too, for a lot of these problems, in terms of time series, you use what the GHI was right now, or just a few minutes ago, or maybe even a couple weeks ago, depending on what problem it is that you're dealing with. In this particular case, we probably want to know what the GHI is over the last 24 hours or so, because that gives us a sense of where we're at. The time of the year, of course, gives you the geometry and the seasonal information, that type of thing. Another thing we did here, and you'll see in a couple of these, is the company was really interested in our being able to use prior models of doing this type of problem at a different location, but perhaps in some way related, maybe in the same latitude or longitude, or in the same weather type of space, and using that prior model, which was potentially built from 5-10 years worth of data, to be able to facilitate learning a model in a different location. So humans do that all the time. A physician here in Halifax, after 4 or 5 years of working with cardiovascular patients, moves to Vancouver, quite a different population, maybe a lot more Asians. They have to morph their diagnostic model a little bit, but they're not starting anew. But that's what we do in data mining, right? We pick up another data set, we build a new model, that type of thing. So this transfer learning thing is really a good thing to do. And it turns out a number of these problems, it does work fairly well. And this is an area, for example, like Shamir's worked on before in his in his research. He was with me. This is predicting out 5 minutes through 60 minutes, sorry, 120 minutes. You can the blue line is the actual, and it's you see, it's over. This is just a day. This is just one day, and it's just simply from early in the morning to when the sun came up to the sun went down, and these are all for the same day, so all the blue curves are exactly the same. But what we did was we backed up in time. So we backed up 5 minutes, and we said, do the prediction 5 minutes ahead for every one of those intervals. And so you can see it's doing pretty well. And one of the reasons why it's doing really well there is because it knows what the global horizontal irradiance is right now. And then it's going to know what it is 5 minutes from now, too, when it's predicting the next one. And then it's going to know what the next one is. And we can all use all the history behind it. We start predicting 15 minutes out, and you notice it's not quite as good, 30 minutes out. By the time we get to 120, it's really not doing so well. And that's the challenge we have. And this just shows that if we do build models, and this is showing the relative error and the amount of data that's being used, time, amount of error and time out to 120 minutes. And the blue curve is when we build a model strictly from the data for that particular location, and the red line is when we transfer data in from another similar location. So the red line is just a little bit less error, particularly when we're well out on the model. So transfer learning does help a bit. And then in this business, even a little bit, just like in the medical diagnostic area, even a little bit's worth a lot, because it's saving potentially millions of dollars in lost profitability in this case. Or at least hundreds of thousands of dollars. Now, with that same company, they're taking all their power to predict solar energy and points in the planet, and then weather. And they thought, well, take this building, for example. If we could predict the weather that's going to be, so let's take ourselves forward a little bit of time, say to about 4 or 5 o'clock this coming morning. If you were able to predict what the weather was going to be like tomorrow around 11 or 12 noon, then you might start doing different things with the HVAC system in this building. In most new buildings, they're all using heat pumps. There's one big heat pump system that pumps essentially heated or cooled, depending on the time of the year, fluid up through a pipe all through the building like this. And then there are other heat pumps on every floor that siphon off that heat or coolant and then pipe it around like this. So the neat thing about this is that if you're on this side, which would be the east southerly side of the building, in the morning the sun's coming up, you don't even have to turn your heat plant on down here. That hot energy coming through the windows, just like that sunroom sort of effect, you know, heats up those rooms, and you take and siphon the heat off that, and you pump it to the other side of the building, and up and down in the building as you need. And some of it you have to bleed it off through the various boxes that you see on the top of the buildings and stuff, to release a bit of heat. And that's all that's needed. So if you can really control that broader environment really, really well with these types of systems, but you have to know what's about to happen to do it really effectively. And you do this probably at your homes to some extent, particularly if you're burning wood and things like this, where you know there's a latency, right, to the whole thing. So can we predict the best HVAC, heat, what's HVAC stand for? Air conditioning, right? What's V for? Anyway, it's heating, ventilation, air conditioning. Action around the building, managing the energy in advance. What's the best action to take right now for, say, 3 or 4 hours in advance? And that's a tricky problem. We had data for about 15-minute intervals from a couple of large buildings and inputs in simulated buildings as well. And we had the time, again, which plays an important role here, the seasonal information. Usually comes down to using the day of the year is the most important thing. The weather, both the observed weather and also the forecasted weather. Satellite imagery again, and that's for the high resolution forecast. And again, the global irradiance, because that's such a big factor. If we can take advantage of the sun, it has a huge impact. I don't know if you know it or not, but buildings use 40% of all energy used on the planet at any given point in time. They're the biggest consumers of energy. So getting control on this is quite important. So the technology we use here are neural networks and some nonlinear optimization techniques. And so this one's certainly a little more complicated. We had to build actually 3 models. The first one was very similar to the project I was just talking to you about that predicted the solar irradiance, but it predicted a whole bunch of weather stuff at a very high resolution, meaning within like 4-kilometer zone, because that's what satellites really can kind of give you. It's getting better all the time, but it doesn't make a lot of sense to do anything much smaller than that at the moment. So the idea is within a 4-kilometer zone to really do well at predicting temperature, wind, flow, and that sort of thing. And then the really cool thing these guys were looking at is that you take the geometry of the building and how it's facing and everything like this, and the roof and the incline of the roof and all that kind of stuff. You take all that into consideration in terms of the impact of the sun hitting the building. And you start to use that information to calculate how much energy from the environment is either hurting or helping you and keeping the building at a temperature that makes humans happy. So the cost function here is 2 things, composed of 2 things. One is how much energy am I using, meaning dollars, and how comfortable are people. So those 2 are they're in conflict, but that's why they're together in the cost function. Right? You got to satisfy both of them. And that's what you want this guy to do. You want this building predictive model to, it's better. I never liked the name of that one. It's actually, I would rather call it just a building control module. And its job is to adjust the plant so that 3 hours, 4 hours from now, you have a really happy bunch of people in the building. Or everyone's gone home for the night, and that portion of the cost function you really don't care quite as much about. But in a well-used building, you know, sometimes like tonight, we've got people here at 7 o'clock doing things. So you have to be able to predict those things or take advantage of calendars, and so objective schedule is the one that feeds into that. The other part of this project that was challenging is that you have to build a building response model. So that is, how does the building react given the external environment, the current internal environment, and the fact that you just walked downstairs and stoked up the engine, the furnace a bit. How does it react? I mean, instantaneously or in the next 15-minute interval. And then what you have to take, once you've got a good model for that, and so how do you get a good model for that? That raises the question. You certainly can't do it on a real building, because what you really have to do there is take and exercise that building under all kinds of conditions, arbitrarily turning the heat up and down and all that kind of stuff to see how it responded. So what engineers do is they build a simulation of the building on a computer, and then they put it through hundreds of years with weather varying and changing externally, with people pushing and pulling the parameters in the system, and they see how the building responds as a virtual building. And then all the data from that we took as such a set of data points with a whole bunch of inputs and with outputs. And then we could use that as a model for understanding how the building would respond. So now we actually had these 2 sides of this. We knew how the building would respond. We had a method by which we could predict what the weather would be into the future. And with that information, we were able to build a model by using this nonlinear optimizer to predict, if we do this now, what will be the result 3 hours from now. And yeah, that was a fairly good-sized project, and it only worked so well at the time that we left it. But we set it up anyway for others. They hired a number of people in the company, and they were continuing with the work. I haven't heard tremendous things about what's happened here yet. You know, I think the practicalities are they're doing a lot of work in that business of, particularly in California. This is a Nova Scotia company doing a lot of work all over the world, and Saudi Arabia and places like this predicting what the solar energy is. And I think that's their bread and butter. This is a challenging one. But other people into this, by the way, are certainly the big companies you might guess, like Johnson Controls, Siemens, really big, and Google actually is, at the time we were doing this, was rumored to be getting into this really big. They really wanted to do a lot in it. And I haven't heard much about that either. Okay, this is more back to agriculture and the environment. This was a project done quite a few years ago, and it was predicting the stream flow rate in some of the rivers in Nova Scotia. And the motivation here is that municipal planners would like to know, for example, if the water rises in a building in the river, you know, is the building plans that they're okaying too close to the river side, that type of thing. And also in the case of drought, and the professor at Acadia, Ian Spooner, who I worked on with this, he was also concerned about global warming and potential impacts of drought in areas and affecting the ecology, and see how low water levels would go. So stream flow rate and of course water levels correlate. Well, stream heights correlate. And believe it or not, people have been tracking stream flow rates all over the world for literally tens of years, up to 100 years in Nova Scotia. We've got records going back like the Annapolis River daily for decades and decades. So there's a lot of data there, and it's easy to get your hands on observed weather data. So you've got observed weather data, and you've got what happened to the stream a day or two in advance after that weather had happened. So one would think you could build a predictive model then, which says, given that the weather has been like this over the last couple of weeks, what do you expect the stream flow rate to be like tomorrow or the next day? And that's really what we were working on. But again, the objective here was to not only predict the flow rate from the weather conditions, there's also some geology involved here too. Like if the area around the stream is all bedrock, then of course the water just runs off. If it's nice, thick, gloomy soil, then the water will penetrate it and act like a sponge, right? And it won't go into the river. So those play a factor too. But the big question here was that we don't have the advantage, of course, in a lot of new places on streams to know what the measurement is. No one's been recording it year after year, but we could go out and record it for a year or two. And then is there a way that we could produce a model, a good model, as if we had 30 years with the data? And this is where the transfer learning work comes back in. So this is the Annapolis River at Lawrencetown. That's our goal, to predict the weather there. We had 30 years of data for all of these locations, but we pretended that we only had like a year or two's here. We wanted to see how well could we do with machine learning, particularly transferring the models. And we've got data, where we could models and data we could transfer from another brook, Shark Brook, and all the way from the Shubenacadie River. Actually quite a different weather system on a local basis and quite a distance away. And it turns out this one worked really well. The blue line here is, again, Lawrencetown, and this is with the years worth of data, and this is showing the mean absolute error measured in cubic meters per second flowing along the river. And it's up around close to 16 cubic meters. And once you've got 5 years worth of data to build the model, now you've dropped that error down to 13, substantially, quite a pretty significant amount. And if you transfer the knowledge from the prior rivers, you can, with only 1 year's worth of data, you get models that are as good as if you had 5 years worth of data. So there's a lot of benefit to doing that. And looking at, this is March, this is a pretty much a full year worth of data. This is the model built from just the Lawrencetown data. This was with 180 days of data, really small sample. And if we do transfer from the Wilmot, another location on the river, then you can see how much better this is fitting versus here, for example. It's even a little better through here. So that's what causes the improvement. And just like you and I, if we were there observing the old Wilmot River and we noticed that in, let's say, late March, when the snow was starting to soften, right, and the ground's starting to become a little soupier and the water hits, then it performs differently in terms of flowing into the river. Versus, and this is one that you may not have thought of, you know those days where it snowed and then it kind of warms up a bit and you get that crust where you walk through the snow and it hurts like heck on your shins when you're doing it? If it rains, if it warms up and it rains, guess what happens to the water there?
Goes underneath.
Well, where you stepped, yeah. But where you didn't step in those big fields leading to the river, it runs off, whoosh, right to the river. So farmers know this too, right? Farmers will know that. Farmers, they'll tell you that, oh, that big rain, that didn't matter. You know, if there's too much frost or a lot of that hard snow on the ground that it can't penetrate, it's just running right off and going into the rivers. It's not going into the groundwater, that type of thing, or even into the soil. So there's a lot. This is a fairly complicated problem, actually, much more complicated than I would have thought before I first got into it. This is highly related. This is, but maybe more important to us, because it's our water supply. This is aquifer recharge. How fast does the well level respond after a good rain, or how quickly will it drop with drought? And again, 30 years worth of data, 1971 to 2000. We had both the well level data and we had stream flow rate data. There were not as many wells as they monitored the rivers and stuff. And we took 17 years to build the models and 13 years to test it. So we would build the models of 17 years with the data, and then we would use it to move forward 13 years over time and actually see how well it did do on those 13 subsequent years. And again, use some transfer learning. This was, interesting enough, was at Wilmot, the place we were transferring data from, but I guess that's where they had this was data from the National Research Center in Ottawa. And yeah, this is not showing a big difference here, but again, there's a little bit of a bump. It's just showing an improvement in terms of the mean absolute error based on an increase in, first of all, the number of years of data that you use to build the models, but also important with transferring in some of the flow rate data from the rivers. So this is a case where if you've got good models for predicting the flow rate in the river, and you add that into the soup for predicting the aquifer levels, it actually helps a lot. And that kind of makes sense. And these are not nearly as impressive in terms of differences. Okay, so this is the project that, again, some of you may know about this one. I worked on it at the Andy Vermeulen's farm over far from where I grew up. He has typically about 15-acre field there, cantaloupe melons, from which he says he supplies most of the Maritimes. Most of the cantaloupe melons that you see in stores in that fall of the year come from his field, which is just over as you're headed up to look off. You look to the right over there, you'll probably see the cantaloupe melon field. It's usually in that area. It keeps moving around, of course. And he kept 6 years worth of melon harvest data, and that's, you know, and actually had it around, which I found in the agricultural community, at least with this type of progress, seem to be fairly rare. And again, we use weather, naturally. The date, again, is really important. For those who've been around agriculture and stuff, you'll know that there's this value called growing degree days. Have you ever heard of that? And Gary could probably tell you better than I am, but basically it's a cumulative sense of the amount of energy that the earth and the sun has put into the soil for plants to grow. And farmers will know that if you get 1,200 growing degrees days, and we're literally telling the degrees Celsius, in the ground, then your carrot's ready to pull, sort of thing. From the date, so you put the carrot seed in, you start counting how many degree days there were between there and now, and if you're at around 1,200, 1,300, the carrot should be ready to harvest. It's a bit of a rule of thumb, but it's one of those things that we use. So that type of information was fed into these models. And again, we used high weather. This is David Koval right here, and myself. That's Andy Vermeulen. This fellow here is Mac McLeod, and he's the principal at Scotia Weather Services, and they do high resolution prediction all the time. Companies like Dexter and big highway firms that lay down cement and asphalt, they call him all the time and say, listen, we got 14 loads of cement. We want to ship out at 2 o'clock and we're going to pour through to 8 o'clock. Is it going to rain in this area? Is that a good idea? And he'll come back, and nowadays, of course, he's saying, no, there's only like 20% chance of rain, so I think you're pretty good, sort of thing. And that's that's his product and service. They count on him doing a really great job on that. So Mac's been at this a long time and does good work in that area. So he was able to provide, again, a 4 square kilometer patch around the field, high resolution forecast. And David was able to provide us with observed weather data fairly close to the field. We actually had 2 sources. One was at the Agricultural Center, and another one was a weather station that David has in Suffolk Mills. It's still a ways away, but not bad. And the job here was to predict the error in the number of accumulated melons. So this is one of these problems where, as you might imagine, the farmer doesn't go loyally every day and see how many melons are in the field. What they do is they count the amount of product that's going out the door, going into the warehouse and that type of thing. And you don't get that data every day. As a matter of fact, during the time we deployed the model, there was 3 weeks, maybe up to 4 weeks, where we didn't get any data. It was rather frustrating. And that's because this is harvest, and they're busy. You know, they're not really interested in this academic project very much at that point. They were, but they're not really. You know, other things are more important. So this was a case of where you want to use time series models, and there's a type of neural network called recurrent networks that work really well in this particular case, what we ended up using. The other thing we use in this situation, something that I think we'll use a lot more of, is just cameras, these field cameras. And they're capable of not only taking pictures, which are very useful. If you look really carefully at this one, what do you see on the right-hand side there? Deer. It's a deer, yeah, that's right. Eating the melons. And what's interesting about this one was that it allowed us to be able to call up the farmer and go, Andy, you know, we noticed that there was a big vehicle going through, because we want to know everything that affected cantaloupe melon growth, right? And these guys are busy and they're into routines and stuff. And you would say to them, you know, so what went on in the melon field in the last couple of weeks? Oh, nothing. We were thinking about irrigating, but we didn't do it. And then you go pick up the camera and you put it on the computer, and there's this thing going by. So you phone up Andy and say, Andy, what's going on? What did you do on, I could tell you the minute, you know, the photograph was taken. And, oh, nothing. Okay, well, just a minute. Here, check your email. Isn't that you? Oh, yeah, we were down there spraying. Well, that might have something to do with the quality of the melons or how the yield and that sort of thing. Yeah, I suppose, but I didn't know you wanted that data. That's how it goes in practice with this stuff. So it was really good that way. The other thing that was pretty cool was these cameras can take, it's not going to be very good up there, I guess. Find my cursor here. Take a picture every hour. And this is every hour for about a month and a half to 2 months. And you literally, so I stuck a stake in the ground here, and it wasn't terribly scientific. It was my little felt marker on the inches on the side, or half inches. But you can actually see the melon grow, believe it or not. Particularly after you see me enter the picture here in a minute. Here we are. And I probably, you know, this is the Heisenberg effect going on here. Of course, I just probably increased the growth rate by exposing it to the sun or something, or reduced it. But yeah, if you really look at the frames closely, you'll actually see this melon creep up a bit. As a matter of fact, it pops a couple times. I don't know if that's something that occurs naturally in a lot of plants, but over a couple of days, it actually goes pop, like this. Maybe it's just moving, but it appears to be like that. And you know, I can foresee that with all the imaging processing technology that we're seeing coming out of Google and others, will literally in the future be able to take, you know, pretty simple images. It may not be in the regular spectrum that we're used to seeing, but various spectra that we can get from our cameras now, and interpret that in very sophisticated ways. And it could be videos like this. So out of this. Out of this whole thing, what we ended up finding, so I'm going to get my cursor back on here. Maybe it'll work now. Yeah. So first of all, this is actual data, actual accumulated melon data from 3 different years. And you can see that these two are fairly similar. So this is running from about the last few days of July right through to into the first week of September. So pretty steady accumulation. And we went with accumulation, and this is one of the things you have to keep figuring out all the time with this stuff, is what's the best target variable? And initially our thinking was, well, we want to predict how many melons grew between here and there. And of course the problem was the data didn't come in like that. You know, you have a data report that was recorded on, say, the 6th of August, and the next one was recorded on the 8th, and the next one was recorded on the 21st. And so all you could do is kind of plot the data like this, and then you set up a model to predict how much of an increase you expect on each of those. And that's kind of a different thing. You're predicting you're not predicting the actual number. You're predicting, not predicting how many you're about to see the next day, because we were predicting 14 days in advance. How many are going to occur tomorrow? How many more are going to occur the next day? We're up to 14 days. What you're predicting is the number of accumulated melons that you expect, which is the same thing, but you have to take the difference between the day and tomorrow's predictions, or between tomorrow's predictions and the next day to get the delta for each one. So all these little subtleties. Now, notice this one. What do you think is going on here?
Bad year.
It was 2011. Apparently that was a really cold summer. I don't know if that's true or not, but apparently it was a really, really cold. Growing degree days were really, really bad. And in fact, there was very poor harvest that year for crops like this. And melons do want a lot of, they're not happy with 1,000 to 1,200 growing degree days. They need a lot more than that. So the approach was to build a model that predicts tomorrow's accumulated yield. And once we had a model for doing it tomorrow, what we did, and this was a bit of a step, we used that model to predict tomorrow's. And besides predicting tomorrow's accumulation, we also predicted all of the parameters that we didn't have. So what I mean is, if there was a parameter such as weather that might be missing, or if there was some other bit of data in terms of like, was it irrigated or something like this, then we made that prediction. Because we didn't actually know what it was, we weren't there yet. And then we would get the results from that, and we would use it to feed it the model for the next day, and we did that repeatedly for 14 days in advance. Now, to some extent, that's kind of like letting lies beget worse lies, if you like. Because we have data that we're predicting that's actually feeding in the model, predicting the next one, type of thing. But it actually worked fairly well. This is an example of what we would send to Andy every morning. And that was another thing we discovered, sending it to, every evening. That's another thing we discovered. Sending this to Andy in the evening was the wrong thing to do. From a computer scientist or someone, an office worker, it might make the most sense. At the end of the day, you get your report and you look at it. At the end of the day, he's exhausted. He's asleep. At 4 o'clock the next morning, he's awake and he wants to see stuff like that. So it took us about 4 weeks to figure out when we should send it to him, right? So that's kind of part of, once you get the knowledge, you got to figure out when to get it to people at the right time. But this shows, the blue line shows our estimated increase in the number of melons. So this is 3,500 melons going up to 4,500 melons in just 2 days. That's the important kind of information that the farmer wants to know. Because picture going out to this field of 15 acres of melons. It's a Sunday. You see in the middle of around the 1st of August, you've harvested maybe your first kind of few trail loads of this stuff, and you're looking at it and going, you know, by next Sunday I've got to have a healthy bunch of guys and girls out here, maybe 2 or 3 flatbed trailers, and really go at this thing. I've got to tell Superstore, make sure that they're aware they're coming, all that kind of stuff. There's a lot of logistics to set up. And then all of a sudden it gets really hot on Monday and Tuesday. And you're thinking, oh, you know, my God, the alfalfa or whatever, I got to irrigate it. So you're busy irrigating, and then Wednesday you wake up in a sweat, and you go, shit, those melons, I wonder how they're doing. You know, it's been really, really hot. So you rush out to the melon field the next morning, and there's already melons starting to rot. You know, it's been that warm, and you're on the phone calling, and so the idea is to avoid that. That's what the beauty of these precision agricultural type of systems. That's one example of why they can be very effective. And so it did work really well this way at the beginning of the season. And he did see information that let him know that the early onset, right, of a high kind of spurt growth. We never did get it quite clear from him just how useful it was, but he did acknowledge looking at it. The red and green is just the amount of our predicted error, and you'll notice it gets wider as we get further out in time. That's how it should be, right? Now this is the end picture on this project. The blue line, this is that, the green line in this case is the prediction, the red and the blue are the variance. It's confidence interval, formally is what it's called. And this is what we were predicting up to here. That's 160,000 melons. Here's the truth. That's what really happened. So we did really well through here, actually. And then what the heck happened there? Well, it turns out what happened there was that he admitted eventually that he didn't quite time the planting. So farmers with this type of crop will plant in intervals, right? They'll plant one set of melons, transplants, and then another set and another set, with the intention that the second set comes on and is ready to harvest at the same time these are finishing up. He acknowledged the fact that his second set he planted a bit late. And due to the weather conditions, for whatever reasons, they were really late. So this was the case of where we were predicting he would have product to sell, when in fact he didn't have any until right here. Maybe he was a little late in getting to the harvest at this point. But then it kind of fit back together again. And now my question for you is, what do you think happened to the rest of it? You can think of this is what actually went out to market.
So just before going on to what the heck happened there at the end, how did it correct itself though? I mean, if the data fed in with regards to the planting, shouldn't that be consistent throughout?
Well, remember, we're using actually what is harvested also as well. So it does have a tendency to eventually correct. Another thing that happened, this is that period where we didn't hear from the farmer for about 3 or 4 weeks. So we weren't actually getting, so this is lie, we're getting worse lie, we're getting worse lie. And finally the correction starts to occur. And they start to come back together again. So it's really common to have what statisticians call that autoaggressive term. It's really the melon count that's part of the input to the model. So at least it tells you what it was just yesterday. And that kind of sets you straight. As a matter of fact, the default model for most things like stock curves, and that sort of thing is called a persistence model. And it's simply, tomorrow's stock price will be exactly what it is today. If you can't do better than that, don't go into the modeling business. So, what do you think happened there? Nope. Paul should get this one. Gary too.
Just got in. They didn't
Pressure's
buy
on, guys.
They want to buy it?
Didn't plant anymore.
Didn't have anything to do with agriculture at all. Because in fact, our prediction in here was actually pretty darn correct.
Oh, it was busy. They were busy. They weren't giving you data.
No, we were getting
But
data.
you're getting, okay, but reliable data?
Yeah,
The store wasn't picking. The store wasn't buying.
the market didn't want
They
it.
just left it.
So I ate a lot of melon, I can tell you. I would go out to the field and I would bring home, my van one time was filled with 50 melon. We were going to my wife's home in Tagan. We took all kinds of melon. Because I talked to you and he said, yeah, he said, seriously. And it's really heartbreaking. Farmers must go through this all the time. They had all these crop and it plowed 50% of his crop into the ground here. Beautiful melons, 15 acres of melons. It's just unbelievable. Yeah. And that happens all the time. You've got to be thick-skinned in that case, I guess, as a farmer, in many ways. But it was the market. And we didn't talk anything about the market going into this project. And in hindsight, that was the stupidest thing I've ever done. But it is so true, So next time around, we have to have some kind of input factors for the market. I don't know how, because here's how subtle it was. Early on, maybe, in here, people at the superstore only want melons that are at least 6 inches, and they won't buy anything underneath. At some point later on, because another plant comes out that's nice and cute, they only want it if it's less than 8 inches, and they won't take anything bigger. But of course, the plants are growing at that point. You get nice, big, fat, juicy 10-inch melons, but nobody wants them. They're too big. Really subtle things affect this sort of space. So that, there's a whole discussion there around food wastage and stuff. The other thing that's important here that came out of this really amplified this issue about weather forecast. Here's a weather forecast we're getting from 2 different sources, working with Mac McLeod. And here's the actual. So this is the error, right? And this is the 14-day prediction. Naturally, the error is getting worse as you're going out further into the future. Notice what the actual data, if you knew what the actual data was 14 days from now, this is how much better you were doing than if you used the weather forecast that you were getting from Environment Canada or other sources. That makes sense, right? But really, the best way to test models is using this data. You're not going to have the true observe weather 14 days from now, you have to use the weather forecasted data. And then you want to see how well it does. So we thought to ourselves, we said, well, okay, why don't we go back and get the weather data for the last couple, the forecasted weather data for the last couple of years to actually see how well we would have done overall. And what we found out is you can't get the forecasted weather from Environment Canada.
So what you're trying to do is determine how accurate the 14 days forecast actually is.
Yes.
Looking back and say, 14 days ago you said it was going to be 2 degrees.
Right. How bad was it?
Okay.
And you can't get that from Environment Canada. The only way to get it is to keep it yourself. There's some good reasons for that. Actually, it turns out that they have numerical weather prediction systems, and if you want it for ecum secum, the way it works is they give a general regional forecast, which is broken down into subregions, and then someone like Peter Coate looks at that and applies a lot of local knowledge and will adjust it just subtly, and that's what actually goes up on the weather, the GC weather website, from which a whole bunch of people, like the Weather Network and CBC and everybody else, gets it. So you'd have to redo all those little bits, or have somebody record all the weather predictions for all those little cities and towns and stuff. So they could regenerate it, but according to the last guy I spoke to, this guy with a really harsh French accent from Montreal, he wasn't going to be able to get it for me, not with a lot of money and a lot of time. So that was disappointing. So if you're ever in one of these projects, you want it early.
It still has to be calculated. It's still being digitally manufactured.
Yeah,
so
and you
it's
could
on
go
some server somewhere.
Well, you could regenerate it, but you'd have to get a Peter Coate to go back and then readjust the numbers for you locally.
I know, but it's posted right now.
Yeah.
So it's.
You could save it. And you would think they're saving it, but they don't.
They don't save it.
No, because it would be too much data. Because, I mean, just think about Nova Scotia, how many little weather reports there are.
Wow.
Yeah.
Well, he's retired now, so he would have time to do that.
You got that new teenager.
So two messages there when you're building models like this to do prediction. You have to really use the forecasted weather. If you want to see how well it does over a long period of time, then you need to know what the forecasted weather was over a long period of time. The second part is it's really hard to get that forecasted weather from any authority. You actually almost have to keep it yourself. Okay, almost at the end here. This is turning to imaging. This is work with John Frost, and his company at the time was AirHive, but now he's working as a subsidiary of Precision Hawk. And this is a Precision Hawk aircraft. And John also had a lot of quadcopters. The problem here is to classify relevant objects from UAV image collages. And in particular, this case was looking for bare ground, weeds, and one of the thoughts was even insect infestations. Now, this aircraft are flying anywhere from 50 to 100 feet in the air, and the shots they're taking of the ground, you can get about 2 to 3 centimeter resolution. So you can actually see berries, that type of thing. And they'll collect maybe a couple hundred images off of 2-3 acre field, and then the computer software stitches those all together. So you can literally zoom into things down to 2 centimeters. And the idea was, could we take this data, this mosaic of data, and predict things like bare ground and weeds and stuff like that. And the motivation here was to be able to spray better, for example, on these spaces. If you just know bare ground, if you know the 20% of your field is bare ground, then you can save 20% of your spray, and now you can do, after 4 or 5 fields, you can do one for free. That's kind of the idea. This is one case where we're trying to predict bare ground. This was one whole field, and this is reddish because it's in what's called near infrared. And the near infrared band is particularly useful because you actually see the amount of chlorophyll that's active in the image. And you can see the variance here slightly, and I know it's not the best projection of the image here, but this is now the classification of that data based on a model that was trained to classify in red bare ground areas and in green areas with viable blueberry crop. And this is just another image which John used as a bit of an advertising piece, and 93% classification accuracy. You can see this was a stream in the area. These are roads. I think we had 11 or 14 different classes of things in the image, which it did a fairly good job on. This was a little more a high-resolution image, and the idea here was, could we classify weeds? And this is a conversion of the near infrared into what's called NDVI. It's normalized difference vegetation index, so it applies a bunch of image processing techniques, really providing a heat map of where the vegetation is. And then there's variance in that. If you do some playing with the pixel data, and from it you can actually generate the image of where, in this case, goldenrod weeds were located. And in Japan, they're doing this type of thing. They give this data to relatively big quadcopters with, like 2 or 3 liter tanks on them. And they actually fly out and with their own localized imaging technology, find that weed, and then they'll go, instead of taking a picture, they'll actually spray it. So, I mean, this is still lab type stuff in agricultural research places and that type of thing, but they're beginning to do that. This is, I think, the last one, and this is Estimage, which a number of people here know about this project that we're hoping to do some more really interesting things on this year. The idea was based on my work with a couple of agricultural, realizing that farmers really are great and they really love growing fantastic produce, but they're terrible accountants, basically. That's what it comes down to. Quite honestly, their pride is in having a great produce, and if they're, I think for some of them, if they're getting through the day and they're relatively healthy and happy, and their families are healthy, accounting is something that was my experience so far. And having grown up here, I think that's probably truer than it might seem. So we were thinking, what can we do in terms of technology to try to help with some of that? And one thought occurred to us, wouldn't it be nice if you could take a photograph of a crop like apples, blueberries, grapes, and be able to estimate from that image how much stuff you might need, like how much of your what's the yield likely to be if you picked it? How many people would you need? How many flatbeds or something like that? You could use it as an estimation tool. So smartphone, transmitting the image back to a server. This is the idea. You take the image with your smartphone, you pass it back to the server. The server has machine learning trained models on it. They've already been trained on a bunch of images for like blueberries, and then can estimate the quantity. And this is the part that a lot of people kind of look at this and go, well, yeah, but you can only estimate the ones that you see. And in fact, that's not correct. I mean, if you, as a human, if you looked at a bunch of these bushes like this, and you just looked at them and then went and picked them, say 10 different groups like that, the 11th one you could look at and you probably could estimate pretty well how many pints there was going to be on there, right? Well, that's what the machine learning technology can do as well. It's really just interpolating between points that it's seen before, similar images it's seen before. So what this system does is that it allows the person who's training the system to go in and notice how every blueberry of sufficient size is marked with a little red dot that says it's a blueberry, and everything in green says those are not blueberries. And then a technique for this case called a random forest builds a model to predict the probability that a pixel is involved with the blueberry. I don't mean romantically, I just mean that how much that pixel has to do with the blueberry. And if it's very much like a blueberry, the value of that pixel, the return is a 1. If it's very little, it's closer to a 0. And once you've done that, you can take, and for a new image, or in this case, this was one of the training images, so naturally it's doing really well. What it can then do is produce a density map, we call it, which is an estimate of how much blueberry-ish there is in every pixel. And then you just count all the pixels. So some pixels might be only 0.01, others like 0.8. You add them all up over the whole image, and that's how many blueberries are in. Or alternatively, that's how many pints, or how many quarts, or how many people you might need to pick it in a day, things like this. And we built similar models for predicting logs and coins. The student who worked on it did a lot of work with just predicting coins initially.
What jelly beans? The jelly bean problem.
Yes, I know. It's a very good one, actually. So there's a lot of problems that fit into this general spatial temporal forecasting sort of space. And deep learning and recurrent networks, which are really great at dealing with sequences and time series, are increasingly being used by them. And I didn't get into telling you about the details of that, but that's it. Yeah. Any thoughts? Questions?
Questions, comments?
For that blueberry one, did you do anything specific to get it to kind of think about the blueberries in the third dimension, the depth dimension? Multiply the whole thing?
No, these systems are just literally trained on taking the images, marking them up.
Just do that naturally.
So this technique relies on a human marking them up like this. These techniques are ones in which you don't actually have to mark up the images. All you have to do is tell the system what the number is associated with it. So we'll stick with blueberries. How many blueberries in the image? So you give it the image and you give it the number of blueberries, and you don't have to mark up the image. And these deep learning type of techniques are capable of actually they're able to develop the really complex representations, almost like your visual system is in your brain, that can map the image to the count of the number of blueberries. And now that's not possible unless you have lots of images of blueberries and their counts. So that's the trade-off here. There's no magic of most of this machine learning stuff. If you could imagine humans sitting down and somehow writing a program to somehow count the number of blueberries in that, it would be probably a really big program and take a long time to craft. The trade-off is that you build, instead of a machine learning algorithm that's able to set the parameters in a complex model like a neural network, and you give it lots and lots and lots of examples of images like that and how many in the count of number of blueberries. In other words, it experiences the relationship between the images and the counts, and it builds its own program, if you like. So that's the trade-off. Lots of images in a machine learning algorithm, or you architect the model, which in a problem like this is really, really hard to do, because you're constantly, and this is what people in image processing did. Let me tell you, there's a lot of people in the image processing world are pretty upset these days, because some of them work 20, 25 years on techniques about how you would solve a problem like this and go on with all kinds of Gabor functions, they call them, and detect edges and do filtration on shadowing and stuff like that, and finally come up with the count. And then there's always something, like if the sun's a little bit more to the left, or it's a little bluer or greener or something, and then you compensate in your program for that, and it goes on and on. And then these guys in the last 5 years come along with these deep learning convolution techniques. They just give it a whole bunch of images. It trains for like 3 weeks, and it does the best that anyone has ever done on the computer system. To the point now where not so much counting, but object recognition and voice recognition is better done by computers now than humans. They'll beat them. Google's systems like that are better than humans.
So something like the clustering of those is anything that is informative is going to be taken on board as informative. So like if it's a bunch of small clusters, I'm probably seeing most of them, but if it's one big mass, I'm probably only seeing a fraction.
Yeah, I mean, if you look inside the networks, what you tend to see is that the representations are really complex and convoluted in many ways, but teasing out for simple problems, you begin to see that these systems have the ability to first generate very small features, like the basic curve and coloration of the outside of the blueberry, in all its variants. Like, this portion has a dark area to the outside, this one has a light portion to the outside of the blueberry. So it picks up all those little sub-features. And then from that, it can take and compose little sub-portions of the curve into, perhaps semicircles of the curve, right? And then the next level of abstraction takes two semicircles, puts them together, and that forms one of the type of blueberries and of a particular size that you're seeing here. And it does a whole bunch of those, all kinds of these features, various layers of abstraction. And the top one takes and puts those all together and says, that object's in the image, or it gives you the count of the number. And that's what we see going on in the visual cortex of our brains as well. Something very similar to that.
Is it compared to the actual yield?
Is it compared to, thus far, we've done only on our simple problems of the coins on the floor. It does well. For really challenging problems like this, it hasn't done incredibly well yet. But it would make perhaps a nice accelerator type problem. Yeah. Christian and I are actually working on now this area, some really deep learning technique, and getting away from this kind of marked up type of thing.
So there'd probably be some kind of correlation between like what the photograph is, and then even though there's stuff in behind or whatever you don't see,
Yeah.
like, and if you measured it, like, you probably could tell from the picture how well actually what the yield is.
Well, one really big problem, Gary, here is how do you get the person to take a good photograph? And it turns out that there's always value in getting to take a fairly standard photograph, but a big part of the challenge is not doing that so much as taking the original photograph like this one. You notice that there's a little bit more sun over here. Maybe if we'd taken that a little bit higher, there might even been some blue sky in it. So there are image processing techniques and maybe even pre-processing machine learning things that you could do to kind of normalize that image to one that looks a lot like the training data that you built the model out of. So the closer you can get it to being like the training data that you train the model on, the better it's going to be able to do it, counting the number of berries.
I guess I was thinking from, you know, if you have like a 30-acre orchard or whatever, like a drone could fly over it and take pictures, and then you could sort of estimate, because I mean it's hard to even do over 30 acres manually. Right?
Well, our thought here with this is that the farmer might take 5 to 10 photographs in different places, and that would all be shipped to the server. It would estimate each one of them and just compute an average.
But you know, if your drone went up and down every row,
and
took video,
just
or whatever,
see it,
like, and then there was something to correlate that.
No, that's true.
So, for your description of the layers in the neural networks, where one does one part of the curve, next assembles it into a semicircle, next assembles it into an actual circle. Seems like a 3 blind mice situation. Where you have, then you have the one head mice that takes all the other mice's information and tries to figure out whether or not it's an elephant.
I guess that's not a bad analogy. If there is some sensory information, though. Let's say they're not blind, but they only have one eye and they can, one only sees things in the red spectrum and the blue and the green. That's kind of a better analogy, is that partial bits of information, the overall scene, are coming in at the ground level, and then, like you say, the emperor mice on top, they can pull those bits together. So you can think about 3 layers of mice, the ones that see red, blue, and green, and then 2 more that package the two together, and then another one on top of those that package the information for those 2. That's the sort of thing that's going on.
Okay. So like, my understanding of this is there's not a lot of middle ground between what you were talking about before, the people who are unhappy with their old techniques, and the machine learning, where there's just things that are just generally better, systems that are just better at learning anything. And you can't really hold its hand and lead it toward the thing that's going to help it. It just has to discover it on its own. Is that right?
Yeah. No, definitely. I mean, the image processing world now is a lot of people who are using these techniques now. And the neat, interesting thing, of course, is that they're discovering in some of the layers that are built, that's exactly like the filter we used to call XYZ that someone came up with in 1995 for discovering curves or edges or some gradation in color, right? And the neural network figured it out because it just saw lots and lots of images. And so that may help someone understand something about nature, which is of value, right? But in many cases, these systems, when they're working really, really well, you don't know how they're working. They're just really complex. I mean, even these systems have these images we were working with. I think we're about, Kristen's now working with satellite shots of cars, actually, in parking lots, because that's a big one, counting number of. So what are the 100 by 100 pixels?
100 pixels, yeah.
So that's the input to a network. That's 10,000
times 3.
Times 3, because you got red, blue, green, right? So 10,000 times 3, that's the input, and the output is a number, could be just one number, which is the count, the number of cars.
Well, actually, we're doing the
density,
the deconvolution too. So
Yeah.
you have 10,000 outputs.
Yeah. If you want to output instead a density map that shows you the center of every vehicle, just highlights one pixel that says there's a car there, car there, car there. Then you just count them. That's even better because it's giving you the location of the cars as well as the count. And what you do then is you take the 100 by 100 images, 10,000 times 3, feed them through a network. It goes in, shrinks down, and then widens back out again and predicts things. So that has a huge amount of memory that's being used. And every one of those have a little active, where they come together at a node has a little function. And this is where very parallel, highly parallel computing systems are being used. GPUs are really successful, and you can also dump it onto Amazon Web Services. Who else is in that business? Well, Compute Canada, a number of others. Microsoft.
You might have several 100,000 or several million different sort of individual pieces in the network that can be adjusted just so, and then
Well, okay, yeah, they take your manual
the desired output. Well,
yeah, how do
you don't, the algorithm updates all of those pieces for you.
There's another, I brought along a couple of things here I'll show you related to this. This is the one that's done quite a while ago, image face morphing. Again, some of you may have seen this. We created a system that, these are 30 by 30 pixel images, and we can take a person's face and just cut out the part that we're most interested in here, just the eyes, ear, nose, mouth. And we took and trained a model on about 130 student faces. And for each student, we had their passport image, kind of, no emotion. And then we had them with an angry face, a happy face, and sad face. And the nice thing about this is once you have the model, you can take and put any person's face, cut out that portion of it, give it to the model, and then turn on the one bit that tells it whether it should produce an angry face or a happy face or a sad face. And then it generates it, and then we just stick it back in this picture. And this is what Mr. Obama looked like when he was talking to Mr. Putin, I guess. You can see. And this was just another random guy. Someone at a conference. This is his sad face, along with some filtering here. Yeah, so those are 30 by 30 grayscale images doing that kind of thing. Yeah, so I mean, you can do all kinds of interesting things with these systems. And again, this was not programmed. What was programmed was the algorithm to map from one image to another image. All those abstractions were automatically generated within the system. And it really does take into consideration a lot of different things like the width of the nose and things and the color, the flesh tones, flesh color. But notice this guy, his mustache is missing because I don't think there were very few people. There weren't very many people in the 130 students that were trained on that had mustaches. So it actually throws his mustache away.
In November next
year. Yeah.
There you go. That's true.
Yeah.
Yeah, I might actually have a beard by then.
I got a slightly silly question. So, all the different examples that we've gone through, I think really interesting. And then, outside of the items that we've talked about, I've seen amazing examples of machine learning being applied to like the creative sphere, like, learning, how to paint like Picasso and reproducing, photos of Danny Silver painted like Picasso, and reading in, the entirety of, a famous author, Shakespeare's work, and being able to produce creative works. So this meme floated past my Facebook feed, like, I don't know, a couple of days ago actually, and this computer science was saying, hey, your kids should be thinking about how to get a job in a space that computers will just not lead it alive. So as somebody who's like deep in machine learning, what are those spaces that machine learning is really struggling to solve? And you've talked about some pretty diverse areas where you're computing solutions around, and then we also get into the creative space. What are those spaces that machine learning really hasn't penetrated well yet?
Yeah. Well, one of the areas that I've become really interested in is that there's been a lot of work on essentially taking things like images or any input, and then learning how to map that to another space, really. Like you can consider the input phases of passports being one space, and then the space of happy faces and sad faces being other spaces. And that mapping type of function is really what we've done. If we want to get more into artificial intelligence, which is a scary thing in many ways, but we need to, in generating those representations that we were talking about that can recognize parts of blueberries and stuff like that, when we do make those representations, ideally we actually want to build them such that we can reason over them. which is a different thing. Reasoning has to do with, you know, planning things out, right? And doing deduction, saying, well, okay, if I have this and this and this, you know, here's maybe something I could do to make life better or simpler. So not many people are working in that space right at the moment. Thinking about how can we learn things so that we can then actually figure other things out. We're just mapping from this space to that space. So that's one area that there's not a lot of work that's been done on. Right now there's a lot of work going on with time series like stuff and stuff that we don't tend to think about time series, like regular spoken word or noises around us, or recognizing music and things like this. You know, to the point where we can now recognize free flowing voice from just about anyone. It used to be very speaker dependent, but now increasingly these types of systems are getting better and better at that. But again, it's just mapping it from there to there. The machine doesn't understand what the words mean. Right? So one of the holy grails for quite a long time has been the semantics in artificial intelligence, actually understanding what those inner bits actually mean, as opposed to be simply something that goes from, you know, X to Y, or X space to Y space. So again, it's in that, you know, the reasoning fits into there too. But you know, if it's in medicine, if you wanted to, we could build models, for example, of X-ray, 3D X-ray data, you know, from fMRI and that sort of thing, and knowing that this person died of lung cancer or a particular heart disease, you know, an occlusion of an artery, and we could probably come up with really, if we had enough data, we could probably come up with some really a great diagnostic tool. But then it'd be certainly useful to understand why it's doing that diagnosis, right? And there seems to be a trade-off there, actually. If you can produce a model that any one of us could look in and say, oh, that's how it's doing it, it's probably not very complicated. Do you see what I mean? Mm-hmm. If it's really complicated and it's doing very accurately, then if it's doing very accurately, it's likely really complicated. Picture like a big if-then structure, you know, and there's really, you know, it doesn't make any sense. I think maybe it's just the truth in the world. That's just the way things are. If it's complicated, it's complicated. And that's kind of the way it is. But getting to that semantics, right, and being able to reason over what we learn, but that's, you know, I think the premise of your question was there are areas now like going back to 2000 with the intermediaries, right? We really trap tourism, for example, bank tellers and all these kind of intermediaries, because we were going to do it all over the web, and those people would be out of jobs, and did reduce a lot of jobs. Now this type of technology has the in banking and places like this. I mean, no one at a bank figures out whether you should have a loan or not. It's all this machine learning stuff. They throw all the variables into it, and it's not based on anyone's notion of whether you're going to repay the loan. It's based on 400,000 people who have repaid loans or have not. And that's what is, well, in reality, that's what tells the person's score. And then a human factor takes over because they see you sitting across the desk. And hopefully they give it to you even if there's a little bit of a question mark.
No.
According to the probably not.
I mean, fintech is one of the fastest growing sectors. With all the finance and investment.
Yeah.
What do you tell your kids to go into?
Oh, yeah. Have you tried to tell your kids things?
What do you tell them not to go into?
Yeah, you have to be very tricky with that one. Yeah. Computer science. How's that? Which none of them had, by the way.
Well, you know, it depends on what wing of computer science. I mean, a lot of the stuff that I did was, you know, I grew up doing, right? Like 20 years ago. I mean, machines are doing that better than I did it.
But just, sorry, my train of thought there, I stopped. So now we could think about potentially systems that are doing not just involved in e-commerce and replacing intermediaries, but we can think about more complex machine learning systems that can automatically make decisions, right? So we don't need that level of knowledge worker. But then if we had a system that could build and recognizing the reasoning components, then maybe the managers wouldn't have a job anymore, I guess. And so it is rather, Oh, by the way, on January the 25th, ACM has a really neat webinar going on. I just saw this today, and it has some of the really big names in AI who are talking about all the fears around AI. Stuart Russell in particular, he was the guy that raised the flag about the military's use of AI. And that was apparently based on an incident which happened in California. This is one of these things that's in the kind of the urban myth category potentially, but supposedly the military demonstrated a set of about 50 quadcopters, which are really small, but quite powerful, and they just sent them up in the air over to a mock village, and essentially what they did was they flew over, and when they saw a face, they shot it. And they just, instead of a camera taking your picture here, bang, you're dead. And they were just pictures of people, of course, but this is a demo that was done, and so there was a big cry, big fear about, they actually have things like this. They're beginning to think of unleashing on populations, right? So the AI community, kind of like you saw around the Manhattan Project, has risen up, and they've had a series of things saying, general population, become aware of what's going on in space. That technology is becoming increasingly autonomous and could be quite dangerous.
So we're a little past 9, and there's still some good food to be had. We want to just kind of thank